Hello, this is Achintya Haldar from University of Arizona. I'll be talking to you on structural health assessment using limited noise-contaminated response information. I have been working in this area over 4 decades. I'll share with you some of my work. Now, the outline of my talk would be, I'll first discuss some of the terminology we use, then purpose of structural health assessment, some of the sensors I'm going to mention, then we'll talk about opportunities and challenges. We conducted both theoretical and experimental investigation. I will summarize them briefly in this presentation. Due to time limitation, it will not be possible to discuss mathematics in detail, but information on references will be provided at the end of this presentation. The basic intent of structural health assessment is to monitor in an automated way to detect initiation of damage or growth of a defect beyond a threshold that can be immediately detected. Then we have to use the difference between monitoring and assessment. Monitoring is the continuous assessment. Offline versus online, ongoing versus on demand. Ongoing could be as a part of overall maintenance strategy. It is multidisciplinary in research and both aerospace and civil engineering application, and we'll talk about it briefly. The major objective of structural health assessments are detection of defects if they are, then classification, location, assessment of severity, and if we decide to repair or replace, then we have to figure out whether our repair was done correctly and whether we detected all defects in the structure. Health assessment is not simply collection of data. Actually, sensors do not measure damage directly. We need to also consider what sensor to use that correlates to the expected damage. Then how to measure them, location of the sensor, sources of power, calibration of sensors. They go out of calibration very frequently. If we decide to use wireless sensors, then we have to figure out there would be some missing data or how to use or apply sources of power. Sometimes we measure data over 24 hours a day. We collect terabytes of data. We have to extract information from that data for structural health assessment. Now, civil infrastructures are most of the time privately owned, and the owner may not give permission to assess structural health from insurance point of view. From aircraft point of view, it is controlled by, at least in the US, FAA, Federal Aviation Industry, and it is controlled by them. Size of infrastructure, types of defect, cracks, loss of area over finite length, corrosion, fatigue, fracture. And since we'll be measuring data, it would be always noise contaminated, and we have to mitigate them properly. We use accelerometer as sensors, but there are other type of sensor people use like strain sensor, displacement sensors, photographic and video image devices, fiber optics, ultrasound, laser scanning, temperature sensors, load cells. I do not have time to discuss in detail, but you can figure it out from the literature. What is the necessity of structural health assessment? If you look at me, I am now bald. I used to have a lot of hair. It is just the natural aging process. And now we use our infrastructure excessively. We overload them. We do not have money to maintain them. Then after natural events like high wind, strong earthquakes, sometimes after man-made events like explosion, and it can be used as a part of overall maintenance strategy. I would subdivide the available approaches into two major categories. One is non-modal based, another one is model based. Non-modal based is basically visual inspection or local non-destructive evaluation. Model based can be static excitation of structure or vibration excitation of structure. Non-model based approach is an old technique. Our forefathers, thousands of years ago, used finger tapping technique to figure out cracks in the earthen utensils. Then, even now, people use hammer after a big snowfall to tap the rails, see if they are damaged or not. The major growth on non-model based technique was developed after World War II. It could be visual testing, penetration testing, magnetic particle testing, radiographic testing, ultrasonic testing. I don't have time to talk about them. Model based approach is now routinely used. It is basically consists of a system. We'll excite it by some input excitation. We'll measure the output responses, and then knowing the input and output responses, we can identify the system, mostly the stiffness parameter of the system, and we'll find out the degradation of the stiffness with time. Now, model-based approach based on static application of loads can have many drawbacks, including it may require large amount of load to cause any deformation in the system, also a reference point. On the other hand, vibration-based approach has many advantages. The amplitude of the load may not be that important. We can use ambient responses. We may not need any reference location, and it can tolerate high measurement error. So again, we use dynamic excitation information. It can be frequency or time domain. We use time domain. Now, one issue we address first, that measuring excitation information can be very expensive and damage prone or noise prone. So we try to find out, or we try to develop an SI technique which does not depend on input excitation. So there could be two alternatives. One is unknown input, another one is known input. We decided to use unknown input. The problem here is that for unknown input, we have two unknowns out of three. It becomes very, very complicated. So to summarize what we discussed so far, structural health assessment could be model-based, we decided, vibration-based, then time domain, and with unknown input. It is very, very complicated problem. So our team developed, we did a lot of work, both theoretical and experimental. I'm showing them, some of them here, and hopefully you can follow some of them carefully. So our intention is to figure out, identify a system with unknown input. And remember, since it will be measured, it will be always noise contaminated, and we have to mitigate that particular problem. We developed several techniques. We'll discuss some of them here. First one, we use iteratively squared technique. Second one is called extended Kalman filter. We use Kalman filter based but extended Kalman filter and unscented Kalman filter will talk very briefly. So to show what we are talking about, say we have a portal frame, we represented it by finite element, we excited it by a sinusoidal load, and then we measured the responses at node 2, and responses is acceleration, velocity, and displacement. We generated this information by computer, and then we identified only using the excitation information, completely ignoring the excitation information, only identified only using generated response information, and we identified the stiffness parameter with less than 2% error. In literature, 10% error is acceptable. Then we added some noise to the computer generated response data, and our error is going up slightly, but it is tolerable. Then we conducted a laboratory experiment. Initially, we tried to figure out how to identify damage, a notch or in the beam. So, but here is the point. We excited that beam using sinusoidal load. We measured the response. We wanted it to be sinusoidal. Then we see offset, slope, and unwanted frequencies. This is called post-processing technique. Always it happens during the dynamic experimentation. We got rid of the offset or the slope. We use different type of filter to get rid of high frequencies, but we could not, and our algorithm did not converge. Then we investigated several sources of error. One is noise, and we figured it out. Noise is not the issue, because all we did, we took computer generated response information, started adding noise, but it always converged. We identified two other. One is, we call it amplitude error. Another one is called phase shift error. Amplitude error, you cannot see it in naked eyes. It is a very amplified version. And when you buy an accelerometer, the manufacturer would give you the data like this. And the second one, we call it phase shift error. And again, manufacturer would give this type of information. We really identify these two major sources of error, and our papers are more referred by electrical engineers than by civil engineers. The main disadvantage of this ALI method is that iteratively square-based method is the structure has to be very small, because we need responses at all dynamic degrees of freedom. We cannot instrument, say, 100-story building. So we have to figure out how to identify a structure with limited number of response information. And we thought Kalman filter would be an ideal method for it. But to implement Kalman filter, we must know the input excitation. Remember, our interest is not using excitation information, so it is not possible. And the second one, that to implement Kalman filter, we must know the initial state vector, which is the outcome of the inspection. So obviously, we have to improve the Kalman filter concept significantly. And what we did, then we proposed extended Kalman filter. It would consider the mildly nonlinear response with weighted global iteration and iteratively square method. And to do this, we have to introduce, we call it substructure concept. Basically, substructure concept is we will take measurement only at only part of a structure, a small part of a structure, and then we can use iterative least square based method to identify the excitation forces as well as the uh, input state vector, but keep in mind it would be noise contaminated. So we use two-stage approach. In the first stage, we try to figure out the based on the available measured information, we took a small substructure and then we calculate the forces, the responses at the node point, and we estimated the stiffness parameter, in this case K1 and K6, and the Rayleigh damping coefficient. We use the two parameter. So in first part, we got the substructure. So in this case, this example shows that we have a three-story building. We measured responses at three dynamic degrees of freedom. And here I have, uh, we identify the stiffness parameter of element 1 and element 2 with very, error is very small, including the Rayleigh damping coefficient. And knowing that, we identify the stiffness parameter of all the element, and it is a little bit higher, but still it is less than 10%. But then when we added noise, 5% noise to the computer generated response information, the error went up to 9%, approaching 10. So what we did at that time, we increase the number of responses from 9 to 10, and the error went down to less than 2%. And it is acceptable. At that time, I contacted a lot of experts in this area, tried to figure out what would be absolute minimum response we need to implement the Kalman filter concept. And nobody said they don't know anything because they never looked at the problem the way we are looking at. Then we simplified, or we verified the method using for seismic load also. As I said before, then to satisfy the community, research community, we conducted a laboratory experiment. For this experiment, all our connection was reconfigurable. We can replace the undamaged element by damaged element. Some of the damage we consider removal of a member, reduction of area over finite length, multiple cracks, one crack, or multiple defects in a system. I'll show you only the result for the when we remove an element, the number 3, and you will find our algorithm can identify the stiffness with this much. Error is about minus 0.8. As you know, stiffness cannot be negative. It indicates the member is not there, and we identify it very accurately. Then we grinded part of the beam. Then we had multiple cracks, then one crack, and then in all cases, we identify those damage location. Now, to implement Kalman filter-based approach, we have to take derivatives or Jacobians. If the nonlinearity in the response is severe, then it may not converge. And then we are looking for algorithm where we do not need to take derivatives. For extended Kalman filter, as I said, we need to have derivatives or tangent. Then non-derivative algorithm include ensemble Kalman filter. What we need to do, we need to simulate responses, and can be very expensive. Then we figure out we can use unscented Kalman filter. It, it would linearize at a deterministic sample point and it gives us the result we are looking for. So let me summarize what we discussed so far. Least square based approach, when the structure is small and then the nonlinearity in the responses is moderate type. Then we use extended Kalman filter. The structure could be large, but with moderate amount of nonlinearity. Then ensemble Kalman filter, I talk, and then we use unscented Kalman filter, and it can tolerate large amount of noise. To show what is going on, I'm going to show this slide. This is nonlinear transformation. We want this and we are getting this. But if we use extended Kalman filter, then you'll find the problem in the given by pink line. But if I use unscented Kalman filter, you'll find that we get very good result. Now, one issue we need to talk about it at this time is called global iteration. In the past, people used one global iteration to implement any Kalman filter-based algorithm. For structural health assessment, if we use longer duration, there is a possibility of multiple sources of excitation, and that can create the problem. In our case, we use very small fraction of a second responses to, to identify the structure. But what happens, it does not provide enough information. So we have to use, we call it multiple global iteration. So for unscented Kalman filter, this is the algorithm we use. But once we subdivide the sample, thousands of a second increment, then we complete global iteration, first global iteration. Since you are going to use multiple global iteration, we then took advantage of that, because as you are iterating, our noise is getting smaller and smaller. So from the second global iteration onward, we use an amplification factor W to increase the amount of noise. And this way, we can predict the behavior very accurately. And here I'm showing the result when we use the amplification factor 10, and it will give you the result very nicely. You can see with 10, we are getting very good result. To verify this particular concept, we took many different structure. I'm going to only talk about this tall structure. We'll identify only responses measured at the substructure level. And then you'll find that if my sampling interval is 0.0001 second, both EKF and unscented Kalman filter would converge. But when I increase the sampling interval a little bit, the EKF would not converge, but the unscented Kalman filter would converge. We then verified the method for seismic excitation, and we took only substructure here and we identified the structure very accurately. So to summarize, we propose several novel concepts, including our iterative least square, unscented Kalman filter, and extended Kalman filter. At the beginning of the inspection, we don't know what kind of nonlinearity you are going to have. So we would recommend always unscented Kalman filter for structural health assessment. As I told you, it is a multidisciplinary in research. I don't have expertise in all the areas. So what I did, I contacted a lot of expert, and I edited a book in 2013. Based on the success of the book, the publisher contacted me and I edited another book just like it was published last year in 2022. It has even people are using now smartphone or iPhone or video, although they are not matured enough. It can be used, they can be used for structural health assessment purpose. Some of you know me that I work on risk and reliability area. I recently published in March 2023 a new method for to calculate a risk of structure excited by dynamic loading applied in time domain. Thank you.